every time the user boots the system or the computer, the malware calls back to your server and connects you back every time, and you could use the resources of the system again. And third is propagates, or what we call it in cybersecurity, pivots through the network. And it looks for other devices on the network that it could hack also, and use its resources to add to its own network and connect back to your own server. Now, starting out with data exfiltration, the main idea is that data exfiltration needs to have an outer server. So you as an attacker need to have a place to store data on, a place where when you steal the data, you should store it on a C2 server. Now, a C2 server is short for command and control, where you could store all the sensitive information on there. And there are different ways to communicate with that C2 server. One of the most common is through HTTP, which is the web-based protocol, which you basically host a web server on your own server, and then you could the malware could communicate with the website and upload all the sensitive data to that website, and it stores all that into a database on your server. And so you could use some sorting techniques to sort of create a file for each machine you hack on your server. That's generally one of the methods. There are many other methods. You could use a decentralized botnet where you could distribute the stolen data on different devices, but this is a bit advanced. The most known is the C2 center, where you steal information and store them on your own server. And this server is not just for storing information; it's also for commands, as we say, command and control. You could mass execute commands on thousands of machines if you have hacked thousands of machines. Of course, this requires a lot of distributed engineering, distributed systems engineering, but as I said, these are professional software engineers that have malicious intent to create these for many reasons, mostly malicious. So one of the examples that we have is Windows operating systems, Linux, and Mac OS. These are the main operating systems on desktop computers that we use. For example, on Windows, it tries to steal your data. Most of your cookies, most of your passwords and emails are stored on your Windows operating system. As we know, the Windows operating system is data intensive system, where it basically stores every activity you do. So that's a rich place for an attacker. It's like a gold mine for an attacker to have information on it. Secondly, Linux. Linux is less of an exploitable because it's a bit more complex to exploit a system that is permission based. It's not. It doesn't have this much windows on it, much of holes in the system so that you could exploit them. On Windows, there's so much configurations that maybe Microsoft would miss some technical issues in it, something in the code base that it has like a privileges vulnerability, or like a memory management vulnerability. But on Linux, that's less likely, as it's open source. So thousands of engineers and coders look at the source code, and at the same time, it has less properties than Windows. Ending up with macOS, which is the least common attacked operating system, yet it is attacked. And yes, macOS has its own malware. We're not going to present these in this workshop. We're just giving you a general idea of what malware does. Moving on to persistent. Persistent is where a malware tries to find a way to, as I said, persist itself on the system. Every time you reboot the system, the memory is wiped, which is the memory inside your RAM sticks. It is wiped, and it is restarted again as you're restarting. And so malware needs to find a way not just to be a part of the memory, the temporary memory. It needs to be stored on the disk. It needs to be part of the system. It needs to be a file there that every time you reboot, it stays in there. And maybe if you format your computer, or maybe change your SSD, some malware like rootkits get access to things like the UEFI or the BIOS or the CMOS system inside your motherboard. And so even though you've formatted the system, the malware is going to persist in there, and it's going to maybe the most of the properties of the malware will be gone when you change the SSD, but the base malware is going to stay in there, and it's going to recall itself again from the command and control center if you install it again, because it's still in there. Okay, so These are different examples. You could take a look at them. On the Windows system, we have registry keys, which is configured some startup services so that every time reboots, the malware starts again. Of course, it does not rely on the default startup APIs on the system. No, it relies on its own. It builds its own libraries to avoid things like antiviruses and EDRs and so on. For macOS, I'm not experienced with them, so these are just some ideas that ChatGPT gave me. I have no idea what are these exactly. What are launch daemons or launch agents? They're mostly Linux reflected ideas because macOS is based on a Unix kernel. So yeah, they have the Linux and macOS have common techniques. Lastly, Linux are the cron jobs, which is like startup services on Windows. These are different ways. Linux, once you get persistent on Linux and you get root access, I think mostly it is the worst one because it's the most difficult to get root access on, but it's the most easy to get persistent on once you get root access. There's so much on Linux that you could do. Okay, so for pivoting, we know that pivoting method where malware tries to not just get stuck on one computer, it's to pivot through your Wi-Fi network. So let's say your home Wi-Fi. Of course, the malware cannot get out of your home Wi-Fi, but once it got into your phone, for instance, it can go to the router and then ask the router what devices is on this network, and the router would happily list them list the devices for the malware because the router does not have a built-in EDR or any machine learning detection method, and so it will just go through the devices, scan them from your own device, and once it finds a vulnerability in one of them, it will jump from your device to the other devices, leaving a copy of itself on your own device, of course. So that's also another very known technique for malware. So these are the three main methods for malware. Now, what is the meter attack? I'm sure if you took introduction to cybersecurity, you know what a meter attack is. A meter attack is a framework that documents every attack possible that ever happened. And we're not talking about specific things like every attack, literally every attack that happened. We're not speaking historically. We're rather speaking in a tactics and techniques methods. Uh, at some point you need a place where you could refer to some attacks that the malware is trying to do, or maybe the attackers are trying to do with the language, with a common language in cybersecurity. And so the meta attack framework was made. Um, we could take a look at it. Let's just visit the website. Let's copy the link. Okay, great. So as you can see in here, the website offers you the ability to visit all the sort of attacks. Let me send it to the chat if you want to serve it yourself. So these are different attacks. We're starting out with reconnaissance. When we gather information about the target, this is considered as an attack because you're not allowed to gather any information about any host that you're not allowed to. Active scanning, for instance, you're scanning maybe the IP address of the website, scanning for vulnerabilities, trying to iterate through the website directories to find anything that could be useful. And moving on from the left to the right, we get initial access and then execution, persistent privilege escalation, and ending up with things like exfiltration, gathering information, which is stealing the information, and lateral movement. So as you could see, it starts from the right as the very first steps that the attacker could do or need to do, which is gathering information about the target and so on. So these are called tactics. So the ones at the top called tactics, and when you open up, what's inside them is called techniques, right? So techniques are under tactics, and in each one you could see a code, right? You could see T1583, which is going T1583. Is going to be the code of acquire infrastructure, and 003 is going to be the code of the technique under that, which is going to be the third one, as you see. So this is just the major attack. It's used intensively in malware analysis report. We're going to see this in a second. And this is, for example, a very known report. As you could see in here, this is one of the professional malware analysis report that is known out there. that uses these codes. So as you see, for example, it says, and cyber actors access it through web shell. And so it's putting the method 15053. So the first the technique, this technique, and the third tactic under this technique. Um, so and then it goes using remote desktop. So it's using a connection through the remote desktop. This is another type of attack. It puts its code and so on. Before we move on from this idea, I wanted to also show you the PDF file that is a professional. This is one of the most professional malware analysis reports I'd ever seen, and this should be your standard when if you're working with malware analysis, hopefully in the future. So you start out by presenting what do you have and a title for what is the name of the malware that you're trying to analyze, what is it exactly, some information about the document and who is it for, and then you put some information about just a summary for non-technicians, for those who aren't like lawyers and so on, if the attacker got caught and sued by the government. And then you put a table of content. You start with an introduction. What happened? What is the story? And some summary about it. How did we analyze it? And then you start with the malware summary, malware delivery, and so on. You put some diagrams here and there. It would help you. And you start with the technical aspect of specifying in detail what does the malware do. So this is your job as malware analysis. You analyze it in a closed environment. And so you put some diagrams where what is going on, what happened, and how does this malware pivot to the network? How does it steal your data, and what server does it send this data to? Yeah, that's all I wanted to show you in this report. Okay, so there are different types of malware. If you took Intro to Sci, I know I'm sure you have heard of it. We're not going to really talk about it a lot, but different types of malware isn't just one type that just tries to steal your data or maybe exfiltrate. These are techniques that are used by malware, but malware have different types. And mostly it is driven by its aim. What is it trying to do, and how does it really attack you? For example, if you speak of the ransomware malware, ransomware is a type of malware that encrypts your files and then blackmails you into, or it's a ransom, as we know. It's a ransom when someone like gets kidnapped by a gang, and then they're asking his family for money. That's a ransom. And so this malware just encrypts your files and then asks you to pay in Bitcoin, maybe a specific amount of money to get your files back. So sometimes these attackers do not get your files back. Sometimes they do. We cannot trust them. And if this ever happened to you, you don't ever pay. Try to find a way to get your files back. If it didn't get back, it's totally fine. Always keep a backup. Not just for ransomware, for any type of malware, because you don't know what this malware could do. It could format your system, maybe. Other types is botnets and bots, which is very known in the world of DDoS attacks, or maybe crypto mining, or maybe gaining views on web pages where attackers hack thousands of devices around the world. And then what they do is that they try to mine crypto on these devices, or maybe try to use them to DDoS a website, or maybe get attention on some website to, you know, to spike the ads on the website and get paid for that. And that's what most of many of the Chinese farmers does. Not the farmers like the typical farmers. No, I'm saying, like, speaking of the digital farmers, the devices that they use. They get thousands of mobile phones. They hack thousands of mobile phones, and then they try to monetize the website's ads through these devices to get paid, and they get paid like $1 per device per click on the ad. And so imagine we have 1,000 hacked devices, so they would end up with like $1,000 easily. So this is what
Plastic ka
one of
na? Awak
yes.
ka ako na ubasi or doctoring ubasi. No,
I
no.
think your microphone is on. Okay. So who makes the malware? As we said, it's attackers, as you've noticed. Attackers or advanced persistent threat groups. It's whether attackers who are maybe teenagers in their parents' houses, or maybe they're just professional attackers under the protection of governments. We're not going to speak of those, but just to have an idea who makes malware. Uh, but many different people makes malware, not just those two. Um, So as we know that malware is has different ways to infect you. Maybe you download something, maybe you click on a link and you download also something. Maybe there is some sort of a vulnerability on a website. Once you visit it, it will steal your data. This is less common, but it may happen. But these are extremely rare situations. Exploit kits, maybe you are connected to a network, maybe you have some sort of a vulnerability, a vulnerable service on your system that that people over your network could exploit. Okay, so let's have a quick idea of how does malware get to happen in real life. Now, and I want to explain this for a reason, and you're going to see it in a second. This is not that complex. If you ever coded Python before or coded in C before, you know what compiling is or interpretation is. Of course, we know computers have their own way of understanding uh, logic or code, which is zeros and ones. Why do we call it zeros and ones? It's because we have high and low. We have a voltage on the computer, and that's why we say zeros and ones. There's really no zeros and ones on the computer. If you ask me, if there's no zeros and ones, it's like saying our brains thinks in atoms. Your brain works by using atoms to think. That's technically true, but that's not the right approach. Zeros and ones are sort of a voltage representation of the computer that we try to create circuits that have a high and low voltage to create logic, outputs and inputs and so on. This is just the baseline of zeros and ones, what we call machine code. Now, computers we cannot understand these voltages, or we could if we spend some time, but it will take very long just to code a basic program. And we have massive projects to code, and so that it will take maybe many years to just write in zeros and ones. So what humans did, they developed advanced or high level languages like C or Python, which gives you ability to write human readable code and then convert it into a machine code, zeros and ones. And how do we convert that is using something called a compiler. A compiler is a type of software. So as you can see in here, in this stage, we code something in C, and then a compiler is what converts this code using some algorithms, some advanced algorithms. It's actually one of the most genius softwares out there is a compiler. It has a pretty creative approach into um, converting this human readable code into actual machine code. And then it goes through a stage of assembly. We're not going to really speak of assembly now, but we're just going to talk about it in a second. And then it converts the assembly to machine code. So this is the stage. It does linking. Maybe it calls some libraries from outside to help enhance the code. And then it converts it to the final product, which is the executable, which in our case, speaking of malware, is going to end up as a malware. Um, so how do we exactly analyze malware? We know that us as analyzers, we receive this only, right? So if you receive an executable, you just need to understand that this executable is not reversible. You cannot just convert machine code into the typical C or Python code. So what do we do is that we do something called reverse engineering, where we read the binary code, the zeros and ones, and we try to make sense out of it by converting it into assembly, which is the closest language to machine code, right? And so by reading assembly, assembly is one of very complex language to read. And so what we do is that we convert it to assembly that gives us some common sense about what is going on. So I will show you an example in a second. Let me show you an example. So let's attempt to write a piece of code, okay? And we're going to compile it in front of you guys. So let's say we have a piece of code, main.c. So let's just so we're gonna import the library. We're just gonna say a hello world thing. We're not gonna make something big. And hello world. Don't really bother yourself with the other stuff, but just know we're trying to print in the console hello world. We're gonna save it and we're going to now compile it. GCC, it's one of the compilers, very known compiler made for Linux. Let's say the output is going to be main, and the file we want to compile is main.c. So it did compile it. Okay. Great. Now we have two files. We have main and we have main.c. So we have two files, main and main.c. Main is an executable. It's a machine code. Now it's in zeros and ones. So when we run main, it's hello world. But when I try to read, let's say I want to read the content of the executable main. So I do micro main. Micro is like a notepad, but for Linux. Main, as you can see, it's just nothing. Maybe there's some information from the compilation process, but mostly it's just nothing, you know. And this is just a hello world program. I know it's nothing, but when it comes to massive files, this becomes more painful. We cannot really make sense out of this. The system cannot. The only way that the system can is by running it into memory, not reading what's its content, because it's just zeros and ones, as you saw. The system couldn't read what that is. We could do something like an object dump. I believe it's dash AI. We could do a GDB main. Yes, please. It's kind of weird. So we could do this disassemble main, which is the main function, and we are trying to get the assembly out of the program. Okay. Now, as you can see, this is how the assembly looks like. So if you go back here, we have wrote a program, we have compiled it using a compiler, and then we tried to read the file. It's just zeros and ones. So what we did is that we read the assembly of it. You don't need to understand any of this. Just so you know, I'm giving you an overview of what assembly is. These are this is the address and memory, and this is the assembly code. These are the instructions like push, move, lift. It's based on the memory structure where there's a stack. You put stuff and you remove it. It's pop and push method. We don't care about this now, but just have an idea what assembly is. Okay, so we have an idea about what compiling or how does it work. This is just a simple overview. Uh, let's move on to the executable format for Windows. Now, most of us use Windows operating systems, and binary files, the final executables that we've spoken here about, is not just one type. They have different types. For example, on Linux, we have this file, the executable file. It's an ELF, executable linking format for Linux. For Windows, we have something called Windows Portable Executable. They both have different structure. But mostly you guys are going to use if you're using the Windows operating system, you're going to use the PE format. It's consisting of this structure. We start off by the DOS header, which contains information about the file size, the magic number, which tells the operating system, hey, this is an executable. Run it directly into the memory. Do not use any other program to run it. Like, for example, I have a text file. It will open it with Notepad. I will load a side program like Notepad and load the information inside the text file into Notepad. But this is a PE file, which I'm going to directly load its instructions into the memory. And the system is going to be able to translate the zeros and ones inside it if it's loaded into memory, not if it's opened in Notepad, because as we saw earlier, executables aren't readable by text editors. So the section table, we don't need to understand any of these, but just so you know, when we are going to convert these into images in a second, where we convert the bytes into images, you're going to see that there is some sort of an arrangement, and we're going to see this in a research paper in a second. Okay, so lastly, I wanted to discuss about how much do we have left? Okay, we have a lot left until the malware machine learning thing. So let's just go quickly through those. Indicators of compromise is a term we use where when we find an activity in an executable that maybe indicates this file tells us that the executable is malicious and it has some sort of a different indicators like the file based. Maybe it's trying to copy itself into places that it's not supposed to be there. It's trying to maybe connect with a server that seems a bit sus, and it's not an official server. Maybe yes, executables, it's a legit executable, it's not a malware, and it's trying to connect to a server. So we need to understand what does it exactly send when it communicates to that server. Behavioral is also based on dynamic analysis, not a static analysis. We're going to see what that is in a second. And what it basically doing is maybe it's stealing some stuff. How is it working on the system? How is it communicating with the system, and so on. So what is static analysis? Now we have two types of malware analysis, or stages to be more technical. Static malware analysis starts by analyzing the file content and inspecting it without actually going to it. But for the dynamic analysis is when you have to run the malware, when you have to actually simulate what is it like to be the victim that runs the malware. Because dynamic malware analysis gives you an idea about how does the malware actually work when it's loaded into memory. The static malware analysis does not tell you that. And so it helps you to understand how does maybe sometimes malware samples are too complicated. The code base that is compiled is too complicated, or the assembly is too complicated to understand in static analysis, that we need to do dynamic analysis. We need to run the malware in a virtualized environment, on a protected environment that simulates a real life machine in order to understand what does this malware do. Okay, so we understood this difference between static and dynamic analysis. For file-based, uh, we have a list of these things. I'm not going to go through them. I don't want to waste a lot of time. And these are different. This is a list of different things you could go through in static analysis. There are many tools that does this, but for now, we don't need to do or go through these. This was actually a workshop by itself, but I try to compress them because we had no time, because we have other workshops to host. But just have an idea also about what static analysis is, so that we could jump to machine learning. Moving on to network-based analysis is maybe we could find some IP addresses inside the executable, which means we could tell that, hey, this is trying to talk to some server. This is another, maybe we could find configuration, like maybe some API keys inside it. We didn't find the server, but we found an API key. Maybe, hey, that's trying also to communicate with the server. That's also another activity. For a host based, we could understand maybe, uh, which is in the dynamic analysis stage. The host based on the behavioral base is in the dynamic analysis stage, where we run the malware and we see maybe it's hooking itself to some process. Maybe it's trying to copy and delete some files, and so on. Moving on to the last one, which is behavioral analysis, which is very similar to host, but more of a compiled process or multi-staged. So behavioral based is where you get what does it exactly do when it runs or connects to at the same time. So you don't just focus on what server is it connecting to, you're focusing on the whole process of the malware process as a whole. Okay, so let's get started with the real, we had an idea about what malware is and what its different types, what does it do, what is an executable file. And so let's try to automate this using machine learning. Now, back in 2011, uh, one of the PhD students, I don't want to mispronounce their name, so I'm not going to say it, posted a paper where they did convert binary files into pictures. And that was a creative method because it helped professionals or defenders automating their workflow. It was one of the very, very first papers to use machine learning in cybersecurity, actually. And it's quite fascinating because it's using it's a very good entrance for you as a security professional to start using machine learning into cybersecurity. So we will train our own model today. I will be giving you guys, I will giving you the samples. We're going to go to Google Colab and we're going to see just an overview of what we're doing exactly. What are the stages? And I'm gonna share with you my blog about this. Um, Great. So that's the whole thing. Let's have an idea about what does this research do. Okay, so going back to the original paper, it's called Malware in Images, Visualization and Automatic Classification. So what do we exactly do in this one is that what we do, as we said before, that malware is, as you see in this diagram, it's a bunch of zeros and ones, right? And we convert these zeros and ones into 8-bit vector. Why 8-bit? I'm going to explain this in a second now on a whiteboard. And we convert the 8-bit vector into a grayscale pixel, and we put this in an image. Now let me explain to you what do we do exactly in a whiteboard. Now imagine with me, you have an executable file, okay? And it's a bunch of zeros and ones like this, all right? Now, before when we made the computers before, we had something called the ASCII table, right? The ASCII table is a reference where what each 0 and 1 refers to, so that computers could understand. Okay, I need to get a proper table. Let me see. Okay, so as you can see in here, these are all the characters that we have. And if you go all the way down, you could find the character number 255. Now, how does this connect to us? How does this connect to the 8-bit Victor that we saw earlier on the research? Now, what does happen exactly is that, let me go to the whiteboard. What we have is that in each computer program, we have whether a 0 or 1, right? So we have two possibilities. Now, what we have is that we have listed every possible combination of any input or character that we want to input. There's much more detail to that, like Unicodes and UTF-8 encoding, but for now, you just need to understand this in order to understand why do we convert it to images and how, and why is it 8 bits. And so we have mathematicians and engineers have tried to put all different combinations, the capital letters in English and the small letters, the symbols and so on, so that we've reached 255 because we wanted something that is mathematically accurate. We didn't want something like 245 because we would need a power to a whole number. So this will be 2 to the power 8, which is going to be equal to 255, I believe, if I'm not wrong. Um, and this gave us ability to represent every character using zeros and ones. Well, how? The way we represent this is by stacking zeros and ones 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 0, 1, 0, 0, 1, 1, 1, 0, 1. This is a byte. We call this a byte, right? Each one of these is called a bit. Okay, this is called a bit. But this whole with 8 bits, we call it a byte. Okay, this is called a byte. Now, why do we care? Because when we go also and try to make a grayscale images, we know that a 0 is black and 255 is white and 127 is gray. How does that help us? That's a great question. If we go into the executable file, okay, and maybe we try to maybe convert it to assembly. Okay, if we go back there into the terminal, and we could see the assembly has, let's say, push. Okay, we want to convert the first letter, okay, P, for instance, and we go there to the ASCII table, and we get search for the letter B small, P, and it's going to be 112. Of course, we're going to convert 112 into some sort of a 8-bit or 1 byte stack. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So we're gonna 1, 0, 0, 1, 1. This is not the right one, but I'm just saying something random just to fill it. And then this will be, as we know from the ASCII table, is going to be converted into 112. Well, we go to 112, we go to the colors, and we know that 112 is going to be between black and gray, which is going to be a sort of a dark gray, right? And so this happens by stacking all of these bytes, byte by byte, right? Sorry, into an image. So we take this image right here, and then we go and take a pixel of this image. We know that images are made of pixels, right? And then we store 112 into a value as a value on this pixel. And this is the whole process of converting it. So we read from the file, we read maybe the letter P from the malware, and then we take this P, we convert it into a binary, and there's much more detail to this, but I'm just giving you the simplest process ever you could imagine, but there's much more details. And so we go and we iterate again and again through these. So P, the word push, P, and then we take U, we convert it to binary, we convert the binary into from the ASCII table to the number that we need from these, according to these numbers, from 0 to 255. And it's useful because 255 is the max number we could reach in colors, as it is the max number of characters into the ASCII table. So this is the method that was developed by these PhD students. And it's extremely useful because you could now easily sort malware families according to just the common behavior between them. And so we're going to take a look at this. Let me show you this in a second. So let's take a look at what are malware families. Now, malware families is when attackers have when different attackers or different group, let's say group A from some government, they have developed a code base, right? This code base have very common functions, very common behaviors. So there's a specific type of malware. So in the future, they're going to add more features to this malware so that it becomes more stealthy. It has things like persistent and pivoting, but the code base itself or the executable is going to be the same. And so what we rely on or trust is two things. The first one is that we trust that the code base or the family of this malware is going to have all of its executables is going to have some sort of a common behavior. Like, for example, let's have a look at what I'm talking about. Okay. Okay. So if we take a look here, this is the for example, let's take agent FYI. This is a malware. This is a version of the malware. Let's say version 1. And then when it was delivered again, as you can see, there is not much different. They're very common. They're very similar. There's some pixels that are changed in the bottom, but it's very similar looking. The width, the height, it's all judged by the size of the file, of course, the amount of bytes we build into the image. But as you see, maybe the aileron gen is also common, the size and how it looks like. So the neural network that we're going to build, of course, we're not going to build a neural network from scratch. We're going to use a pre-built one. We're going to see this in a second. But if you could see that there's common patterns between them. Also, like, let's say DL platform B, these are different executables. These were binaries by itself. Each one was an executable. We converted to an image, and visually we could see that they're very similar. So the malware kind of recognized them easily. Okay. Now, there's really nothing in the slides to show you. It's just research level stuff. So let's go and move on to the I think I had the blog in here. Let me just in a second. Okay, great. So I've wrote a blog about it if you want to read it or go through it. But for now, we care about the notebook. I'm going to share this with you in a second. Let me just copy link address. And I'm going to run these in front of you now. Now, clear selected output. Clear selected output. Okay. So what we have in here is a code that I made for you guys, so that we're going to go through it. The very first thing is that we're going to download the before that we're going to check if we're running GPUs. We use, of course, graphical processing units because they're much more efficient than CPUs. They run like thousands of CPUs at the same time. This is the perk of being a GPU. And so you could go to runtime and then change runtime type. On my notebook, I have already set that up. I'm going to share the link with you now in a second, but let's just explain this with you guys, and then I'm going to share this with you. So I have chosen a GPU for faster training. And so after that, I clone the data set from the Kaggle. We don't need to know what this website is, but it has many malware samples, and one of them is this mal image original, which has already converted for us the binary files into images. So let's just clone it. This is Google Colab, of course, and it's connecting the runtime, and it's cloning the samples we have. So it's going to download it. Of course, while it's downloading, let me show you. I have it on my own machine. I'll show you the malware sample. So this is the malware families we have. These are different files. This is inside the compressed file. For instance, let's take a dialers.c and see what's inside it. Let's go inside it and open up. And as you can see, there are different executables. And what you could notice is that there is a common pattern between all the executables. So each one of these images was an executable file that had its own function, that had its own version, right? Let's say this is the version 1, this is version 2, this is version 3. And so attackers were, delivering thousands, maybe hundreds of versions. And this is what we got from them. Each image was a version by itself. Okay. And if we could open one of the images, I'm sure it's going to blur it because it's defined as a software like this. You could see the pixels inside the file. You could see each pixel was a byte, of course. You could see there's a white pixels, there's a gray dark, and so on. But it was, as you see, it's very clear to see the pixels as the image is very tiny. It's a 75 by 75 in scale. Great. So we have all of these families, and we're going to start training them. So let's make sure that the compressed file is here. Great. Let's unzip the file. And as you see, it's unzipping it. It's uncompressing the file that has thousands of images under each family. Let's just wait for it to finish and make sure that it's there. I'm sure I believe it's finished because yeah, this one is the last. So, okay, great. So let's do an ls, and we could see that the malware families under this file that we have is there. Okay, great. So let's install a library. We're going to have a look in a second. What are we doing exactly in here? So we have split folders. It's a library we're going to use in Python. We're going to take a look at what are we going to do exactly in a second. Let me just run this, and I will explain to you what we're going to do. Just going to finish. And yeah, is it done? Yeah, it's done. Great. So we do ls, and we could see that there's another folder that was made. Inside it, there's a test, train, and val. Don't care about val. Just focus on train and test. So let's go back to my blog and see what do I mean by all of this. So it is somewhere. Yeah, this one. Good. Now, as we said before, the process that we go through is we convert 8 bits or 1 byte to a vector, and then this vector we convert it into a color. Okay, we have explained this. Now, what we're gonna do first is that we're going to where is this all array operations? Yeah, this is just an introduction to Python machine learning. We would need nope. Okay. Convolutional neural networks. Nope. Not this one. Putting it all together. Okay, so what we have in here is that we have a data. Under data, we have train and we have test. Now under train, we have malware simple, or sorry, images. And under test, we have images. As you could notice, the images under train is more than test. Why? Because before we have a model, we need to train the model, right? In order to have a model, we need to train it. So we give it about 80% to train, and we're going to see this in the code in a second. And then we test that by using maybe 20%. It's because we want to give the most of the samples we have to the model. Now, why do we split them? Because when you run the model or test it, if you put everything, the test and the train for training the model, you don't have anything to train the model. And at the same time, you want the model accuracy to be high, so you want to give the most to training. And so at the same time, you want to test it, so you want to have something to test the accuracy of the model. Okay? And the more you add to the training data, the more you have accuracy in the model. This is very known in artificial intelligence. I'm gonna show you this down here somewhere. It is in Google Lab, I believe. Okay, so what we did here is that you don't need to really know Python for this workshop. I'm just going to go through it and read it for you just to give you an idea about what this machine learning method is going to do. We create a file called data split, and we read from this file called mail image paper dataset images that we have downloaded earlier. And if you could notice in here, we have a seed, right? We have a seed and a ratio. The ratio is the directories we have, which is 0.8 to 0.2. 0.8 is basically the amount of values or the portion that should be inside, which is 80% of the samples that we have should be inside the training. And then the third file we remember is val, which is the one that we're not gonna use. We don't care about now. And then the 0.2 is the 20%, which is going to be the amount of data that we're going to use for testing. Now, we have did the splitting, the basic splitting. We have the files. Now let us run the training. So while it's running, I'll just go all the way down. Let's just wait for it to. It's gonna take some time. I hope we don't get any errors. Okay, so what it's doing is that it's taking patch by patch. It's taking the thousands of samples and it's taking it 500 by 500 by 500 and training it in patches or bundles so that we could arrange the training and make it much better and readable in the output itself. So let's go back to the code while it's running and just have a quick look at it. It's a very simple piece of code. So we have divided them into 80% for training and 20% for testing. The pre-processing is when you get images ready for being loaded into the transformer model. We don't need to understand all this also, but just so you know, we are using a pre-trained model to build above it. So I'm sure it wasn't the research here. I'll just look it up. It's much easier. ResNet. Okay. I need to find the architecture diagram for this model because it's the one that we're going to use. That's kind of weird. It's totally fine. Yes, this one. Okay, so as you see in the Rust 50, yep, this one. So imagine with me, this is the place where we have an input, and this is the place where we have an output. Okay. Now, in the middle, we will have different layers. We don't care about any of these layers, but the last one, which is the grid size reduction. We're gonna use only the last node, the last layer. Of course, this is not the right image, but just to give you an overview how a neural network looks like. We're going to freeze all of these, the last layers, because they are pre-trained, and we're going to only use the last layer, the layer number 50. We're going to freeze the 49 past layers. We're going to use the last one. Okay. So we're going to read this into the code in a second. We're creating the data loaders and so on, defining the model. And so we are importing this model called, as you see, Rust 50 from here. And we're saying that it's going to be the default. All its weights is going to be the default. And then what we're going to do after we set up the models, we made the data sets, we're going to do a setup for the training. All of this code could be simplified, but I'm just doing it for an improved output. Okay, so the training function, we also don't need to do this to understand any of this. Just to give you an overview of, I'm looking for, yeah, the training loop. Now the training loop is we take a batch of specific amount of images, 500 images, let's say, and then we iterate through them through an algorithm by the model, and we try to store the output, and we output the training accuracy and the testing accuracy by every patch we finish. And this is a loop. So if we go down here, we could see that we have about 10 epochs or 10 patches. Each one, I think, has 500. And as you could see, the training accuracy as we started is 76% and 85 for the test. And it increased through the time we are training the model. So let's just wait for it to finish. Now, of course, anytime we were trying to develop a malware, and that is similar to these malware samples that we are trying to train the model on, it needs to be similar to the malware. It needs to have very similar patterns to the malware families we have. Because if it was a brand new malware, it wouldn't have, the model wouldn't be able to detect it, or it will give false information. Okay, great. So we're done now. This is the training progress, or how the training and test relationship through the time of training was. And as we see in here, through the time we started first epoch, or the first batch, until the 10th batch, we have divided the thousands of images into patches, and we could see that the training had increased significantly as the test increased with it a bit more. But the test is it's very similar to training as we progress more to the end, or we increase more training data. And this is the whole idea of training. This graph represents how good our model is. That's all. And in order to use this model, we could go to the files, and the model is called best model.pht. Of course, it's named from the code .pth, which is the model that we could use. This is the final model with an accuracy of 94%, as we see. Good. So this is the whole training process. I give you an idea about how does CNN work. Sorry, the training process work. We have used RusNet 50, which is a pre-built network or neural network that we have frozen most of its layers and then used the last one only. Okay, great. So I think this was everything for this workshop. I hope you have learned something at least, and you have interest in malware now eventually. And if you have any questions, please go ahead and ask. If you don't have any questions, you could proceed to leave.